Okay, so now I'm going to use the mean value property to prove the weak. So I'm going to use the mean value property to prove the weak and strong maximum principle for harmonic functions. So this is theorem 3.5, and it says the following. Suppose U is harmonic. Suppose U is harmonic on the connected set omega. So it's a harmonic on the connected set omega. And that U is twice continuously differentiable, which I'm going to abbreviate as diffable. So in other words, you can take a double derivative in the x and the y variable, a double x derivative, a double y derivative, and both of those functions are continuous. Then the following two things are true. One is going to be the weak maximum principle. We have seen this for the diffusion equation. It says that the maximum over omega, over the entire domain, so this is omega and its boundary, U is equal to the max of the max of U on its boundary. So this says that the maximum, that there is a maximum on the boundary. And two, so this is the weak maximum principle. The weak maximum principle says that the maximum occurs on the boundary, but this alone doesn't preclude the fact that the maximum might also happen in the interior. The strong maximum principle is basically going to say, no, actually the maximum can't happen in the interior. So the maximum says, the strong maximum principle says, if there is an x naught, y naught in the interior, of omega such that U of x naught, y naught, sorry, going to have to come down here on the line, is equal to the maximum of U over omega, then U is constant. Okay, then U is constant. And constant functions are technically harmonic functions because, they're all of their derivatives are zero. But, we don't like to think about them so much. They're not interesting. So the weak maximum principle says the maximum must occur on the boundary of omega, though it might also occur on the interior. The strong maximum principle says, actually, no, it can't even occur on the interior unless it's constant. So it's very important that our domain here is connected. Let's say this is omega. The weak maximum principle says, okay, we know there's going to be at least one point where where the maximum of U on this whole domain, including the boundary, there's going to be one point on the boundary where U gets its maximum. But you know what? Maybe there's also a point here where U attains its maximum. That's what number one says. Number one just says the maximum occurs on the boundary. The strong maximum principle says, wait a second, actually, if there's a maximum here, it means U is constant, and so it's equal to whatever the maximum is all over. Okay, so let's prove this. I'm going to draw this domain omega just to kind of help with the illustration. So this is omega, and like I said, it's going to be helpful that the domain is. It's going to be helpful for us that the domain is connected. That's a crucial property here, and you'll see why in just a minute. Okay, so first let's assume, I'm going to prove the strong maximum principle, and then from that I want you to figure out how you can prove the weak maximum principle. There's also either a homework or a discussion, or one of the discussion questions where I ask you to prove the weak maximum principle using a perturbation method. Okay, so let's assume that there's a maximum here. So if U attains a maximum at the point x naught, y naught, then by the mean value theorem, so let me actually say this a little bit differently, because it's not by the mean value theorem what I'm about to say, but I will be using the mean value theorem. So let's just write it like this. Sorry about that. Assume U attains its maximum at the point x naught, y naught, which is in the interior of omega, which is sometimes denoted like that. Okay, so let's assume that U attains its maximum at x naught, y naught in the interior of omega. That is, it's not on the boundary, it's in the interior, because that's what we want to prove here. If it's in the interior, then it's going to be constant. So let's assume that that happens, and we're going to prove that it's constant. Let R greater than 0 such that the disk of radius r centered at x naught, y naught is in the domain here. So these are going to be the points xy such that x minus x naught squared plus y minus y naught squared is less than r squared. Okay, so we're thinking about a ball like this. Okay, so points that are closer to the boundary, this ball is going to be smaller. But, you know, we're here in the middle of the boundary here, and so what we have is a big ball around the point here. By the mean value theorem, we know that U of x naught, y naught is equal to 1 over pi r squared times the integral over this disk of the function U. That's what the mean value theorem says. So what we want to do is we want to use the mean value property here to prove that U is going to be constant on this ball here. And the basic idea is, let's imagine that there is a point here. We'll call it x prime, y prime in just a second. Let's imagine there's a point there at which U is less than the maximum. Well, since U is continuous, there's got to be some ball over here on which U is less than the maximum. Okay, and if there is a ball on which U is less than maximum, notice what's going to happen. The maximum that you can get is going to be that. Let's say it's 17. Let's say that U at U of x naught is U of x naught y naught is 17. That's the maximum. The integral of U on this portion that doesn't include this little ball right there, U is less than or equal to 17. It can't. There's no part here where it's greater than 17. So if you have a part here that's less than 17, but the biggest it can get at any other point in the ball is 17, what this means is that the overall average value has to be less than 17. Okay, so think about that. I'm going to sort of explain it with formulas here in a minute, but think about what I'm saying here. I'm saying if we know that the maximum value you can get on this ball here is 17, then it's average, and we have some portion here that's less than 17, then the average value has to be less than 17. Okay, like if I have 10 numbers and I know all of them are less than 17, and I know 2 of them are less than 17, that means their average has to be less than 17. Okay, that's essentially what we're going to say here, but just a continuous version of that. So assume there is a point x prime, y prime in D where U of x prime, y prime is strictly less than U of x naught, y naught. By continuity, there is a disk, I'll call it D prime, which is a subset of D, a subset of the bigger one, such that U is less than U of x naught, y naught on D. Okay, Well, so now what's going to happen? I can look at the integral of u over d. I can split this up into two integrals. I can look at the integral of d set minus d prime, so that's everything except for d prime, plus the integral of d, d prime, I mean, u dA. Okay, now this right here, since u is less than or equal to 17, or sorry, less than or equal to the max, I have 17 on my mind. Since u is less than or equal to the maximum, it means this integral here is going to be less than or equal to u of x naught y naught, which is the maximum of u. Remember, u of x naught y naught is a place where u allegedly attained its maximum, so the integrand is less than or equal to u naught times, is less than or equal to u of x naught y naught, and then it's going to be times the area here, because if we replace u by a constant here, it's just going to be the constant times the area of d minus d naught. So I'm going to use like absolute values here. That just means the area of this region here that's in D that doesn't include D prime. Okay, well hold on a second, because actually we're assuming that u on D prime, sorry I should say D prime here, we're assuming that on D prime u is strictly less than the maximum. So I don't have a less than or equal now, I'm going to have a less than. So this is going to be less than u of x naught y naught times the area of D prime. Okay, well I can factor out the u of x naught y naught, but the area of d minus d primes plus the area of d prime is just equal to d. So this is equal to u of x naught y naught times the area of d. Okay, so what do we say here? The integral of u over d is less than u of x naught y naught times the area of d. So if we just divide both sides of this inequality, and forgetting about these intermediate steps for now, this says 1 over the area of d times the integral of u over d is strictly less than u of x naught y naught. Okay, but by the mean value theorem, this is equal to u of x naught y naught. So in other words, we're saying u of x naught y naught is equal to this, is less than, strictly less than, u of x naught y naught. So in other words, we're saying u of x naught y naught is less than u of x naught y naught. Obviously that can't be true. Okay, so what we can conclude then, and I'm going to basically erase all of this, what we can conclude then is that there is no point x prime y prime in D where u of x prime y prime is less than u of x naught y naught. That is, the conclusion is that u is constant on this disk, and it's equal, u is constant on this disk, and it's equal to, u is constant on this disk, and it's equal to the maximum u of x naught y naught. Okay. Unfortunately, I can't keep that up. There's not enough room. Okay. Okay, so now what I have, I'll mention, I made another mistake, so I think I'm coming back to where I wanted to come back, but I know this probably looks different than what it did just an instant ago. So what I've proven is that for a generic point at which u attains its maximum, on any ball around that point that's included in omega, u is going to be constant. Okay, well now I can take, really that should be centered, but I messed up the drawing. So then u is constant on this whole ball, so it's equal to the maximum there. Now I can draw a ball like that, so it's constant. I can apply the same argument to this ball, u is constant there. I can, u is equal to the maximum there because u is constant on this ball. I can apply the same argument to that, and it seems like we can probably just, do this chain of balls all throughout omega and prove that going from one point to another point, I can get from one point to another point to prove that u is going to be constant everywhere. Now maybe you can get something like that to work, but there's always going to be a chance that you have something like this. You have this really small tube in which case the boundaries of these balls get smaller and smaller and smaller, and now it's not so clear to me how are you going to make some argument like this work. Maybe you have something like this, and then you open it up like this. So you have some like a pair of lungs or something like that. Now getting this chain of balls to go through there, if you have this boundary getting very, very small, maybe it'll work. Maybe you can figure out a way to make the argument work and share it with me in the discussions, or share it with the whole class in the discussions. So what I'm going to do now is I'm going to use some topology here. I'm going to say that omega prime, so my whole set is omega, I'm going to say omega prime is equal to the set of x and y such that u of xy is equal to the maximum of u over omega with its boundary included. Okay, so I'm going to make one claim about this. Omega prime is open. Omega prime is open in omega. Okay, what this means is that aside from the points on the boundary of omega, for every point, let's say this is omega prime, what this says is that for every point in omega prime that's not in the boundary of omega, for every point in omega prime that's not in the boundary of omega, we can draw a ball around that point, and that ball is in omega prime. Okay, well, why can we do this? Well, if this point is in omega prime, it's in the interior of omega prime. That is, it's not on the boundary of omega. If you have some point that's in omega prime, and I draw a ball around it, I can draw a ball around it that doesn't go outside of omega. U is at a maximum there, and so by the argument that I just went over, U has to be at its maximum on that whole ball there. So that whole ball there is in omega prime. Okay, so this tells us that omega prime is open in omega. So when I say open in omega, this means, relative to what's called the subset topology, or the subspace topology. So what it's saying is that, as a set of R2, omega prime is open except the parts of its boundary that coincide with the boundary of omega, those might be in omega prime as well. So like this point right here is in, we could say that could be in omega prime, and it is in omega prime, as this proof will show. Okay, so now what we're going to do is let's imagine that we take any point in the boundary. So if we take some point, I'm going to call it x naught, y naught, that is in the boundary of omega prime, and in the interior, let me write it like this, the boundary of omega prime intersected with the interior of omega, so it'd be something like this. All right, so like that point right there, then u of x naught, y naught is equal to the maximum over omega of u. Okay, why is that? Well, any point that is in the boundary of a set, if we're dealing with connected sets like this, any point that's in the boundary, there has to be a sequence in omega prime that converges to that point. Okay, there has to be a sequence in omega prime that converges to that point. Well, I know at all of these points, u of omega, u evaluated at each one of those points is equal to the maximum of u over omega, because they're all in this set omega prime, and that's what it means to be in omega prime. So since u is continuous, it means that u must be at its maximum right here on the boundary. So now what we have a point that is both in omega, a point that is both on the boundary of omega prime and in omega prime. Well, that contradicts the fact that omega prime is open. If you have a point in the interior of omega that is on the boundary of omega prime, it cannot be in omega prime because omega prime is open in omega. Again, what does it mean for omega prime to be open in omega? It means if you look at the part of the boundary of omega prime that's in the interior of omega, we know that it does not contain, that omega prime does not contain that portion of the boundary. But this argument here says, well, actually, if this point is in the interior of omega and on the boundary of omega prime, it means that that u is equal to the maximum at that point, which means that point is in omega prime, which means u contains its, or omega prime contains its boundary in the interior of omega. Again, that contradicts the fact that omega prime is open in omega. And so therefore, omega prime has to equal all of omega. Okay, so this is sort of a overview of that last part is an overview of a proof that says if you have a connected set and you have a subset that is both open and closed, that subset is equal to the entire set. And so omega prime is both open and closed. It's open for the arguments that we gave. It's closed because if you take any sequence of points in omega prime, it's going to converge to a point in omega prime. That's one of the things it means to be closed. And so therefore, omega prime is open and closed, and so it's equal to omega. Okay, that was a strong maximum principle. From that, try to prove the weak maximum principle.